Have you noticed how rarely you drive the speed limit? You accelerate on open stretches, only to slam on the brakes for traffic seconds later. Imagine you took that exact same route and arrived in the exact same amount of time, but you did the entire drive with your cruise control locked on a single, unchanging speed. That constant speed would be your true average. Finding that value is difficult because your speed changes at every possible moment, leaving you with a limitless amount of data to track. If you watch a speedometer, the needle doesn't step neatly from 30 to 40, it glides, shifting at every tiny fraction of a second. Because that value never stays still, you can't just pick 5 or 6 random readings from your dashboard and expect them to provide a true average. To take a chaotic, constantly shifting reality and distill it into a single number, we need a mathematical tool designed for a world in motion. This chart shows exactly how a car's motion changes during a trip. We track time on the horizontal axis and speed on the vertical axis. What we get is a messy, bumpy curve. Let's start with the easiest possible scenario to make sense of this, moving at a perfectly constant speed. If you travel exactly 60 miles an hour for 2 hours, simple multiplication tells you that you drove 120 miles. On our graph, that simple multiplication takes a physical shape. The distance you traveled is exactly equal to the visual area of this solid rectangle. But we know our actual speed has bumps and dips. We can't rely on simple multiplication to find out how far we've gone, because there is no single rectangle to measure. So we try a mental hack. We pretend that our messy trip was actually a series of short, constant speed jumps. By chopping our journey into these blocks, we can calculate the area of each one, and then add them all together to estimate our total distance. There is a flaw with this estimate. These blocks are clunky. Their hard corners stick out over the true speed curve, and they leave empty gaps underneath it. To fix this, calculus gives us a way to refine our approximation. We make the time intervals smaller and smaller. As the rectangles get incredibly thin, they pack tightly together, following the exact contours of the trip. This process is called integration. It is the act of bringing all these tiny values together. As we let those time intervals shrink down towards zero, the microscopic rectangles melt away, leaving a smooth shape. That exact shaded area represents the precise distance your car traveled. Integration takes an infinite number of microscopic moments and adds them up to reveal the complete big picture accumulation. We have our exact total distance. Now we return to our original goal, finding that single constant cruise control speed. We can find it using a visual trick. We take the bumpy, mountain-like shape of our total distance and reshape it. The high peaks of our fastest moments flow into the low valleys of our slowest moments, forming a perfectly flat rectangle across the exact same amount of time. The math follows a straightforward rule. If you divide the total area of a shape by its width, you get its exact average height. The height of this newly flattened block represents the answer we've been looking for. It is your true average speed. This process works for any changing variable. Because the sun moves and clouds drift by, the energy a solar panel generates fluctuates all day long. Scientists use integration to find the total energy gathered over the day, dividing that by the number of hours to find the average output. Meteorologists rely on this to track shifting ocean temperatures over a season, and engineers use it to predict the massive fluctuating demands placed on city power grids. Integration is how we turn a chaotic reality into clear, usable answers. What constantly changing thing in your own life would you like to find the average of? Let us know in the comments.